Okay, well, welcome back to Calculus Conundrums, application of derivatives by the perfect square. Feel free to subscribe to the videos. I'm going to continue in this video on optimization problems. So in this problem, we have a steel drum that's in the shape of a right circular cylinder, and it's required to have a volume of 100 cubic feet. And we want to find the radius needed to minimize the required material. So basically, let's focus on this side first. So let's talk about the area of the cylinder. So what we want to do is we want to minimize the surface area of the cylinder. So let's talk about the surface area of the cylinder. So this cylinder would have the side portion, which would just be this part right here, and then it would have a top and it would have a bottom. Now the top and the bottom are just circles, so we can talk about their areas pretty easy. You would just have pi r squared on top and pi r squared on bottom, and so you have pi r squared plus pi r squared, so you get 2 pi r squared. Now, but what about the side portion? Well, let's say you took a soda can and you cut the top out of it and you cut the bottom out of it, and then you cut that cylinder straight down like that and then unfolded the side. Well, then you would get a rectangle like I've got drawn right here, and then the dimensions of that rectangle would be the height, which would be the distance from the bottom to the top, and then the circumference of the circle, because basically this dimension right here is just the distance around the circle, and circumference of a circle is 2 pi r. So we know that this would be just 2 pi r. So now the area of this rectangle, which would be the area of the side of the can, would be h times 2 pi r, or 2 pi r h. So now that we put that together with the area of the top and bottom, and we get 2 pi r h plus 2 pi r squared. Now, the problem with this is my primary equation, okay? But the problem that I have with this is I've got two independent variables here. I've got r and h. So what I need to do is figure out how can I eliminate h. Well, we know from over here that the volume of the cylinder, which is the volume of a cylinder, is pi r squared h. So the volume of the cylinder must equal 100. So now what I can do now is I can divide both sides of this equation here by pi r squared, and I can get a value for h. So then I can take that h and plug it back into here and simplify it. So let me show you that over here. I probably didn't do this in the right order for you, but let me show you what I did here. So here, remember what I had get this thing to work for me. Okay, so what I had is I had 2 pi r, and then I wanted to multiply it by h, so the h being the 100 over pi r squared. And so now if you simplify this, all you have to do, you can cancel the pi's, and then the r in the numerator would cancel with r squared, giving me an r in the denominator. So all I'm going to have is 2 times 100 on top, and on bottom I'm just going to have r. So I have 200r plus, of course, the 2 pi r squared. Now, that's my area, and since I want to optimize that area, I need to take the derivative. But before I take the derivative, let me go ahead and rewrite this using negative exponents. So 200 over r is 200 times r to the negative 1. And then, so if I differentiate that, if you differentiate 200 to the negative 1, you'll get minus 200 to the negative 2. And if you differentiate 2 pi r squared, you'll get 4 pi r. So basically what I've got here is I've got the derivative is minus 200 r to the negative 2 plus 4 pi r. And we're going to set that equal to 0 to find the critical numbers. Now, so I'm going to set that equal to 0. So if I set this equal to 0, let's just focus on this portion right here. Okay, so now what I can do is I can multiply each term here by r squared, and that way it'll cancel the r to the negative 2. So I'm going to multiply each term on the left by r squared, and of course then I'll have to multiply the 0 on the right by r squared. And then when I do that, r squared times minus 200 r to the negative 2, it's just going to cancel the r's, and I get minus 200. And then when I multiply 4 pi r by r squared, I get 4 pi r cubed. And then 0 times r squared is 0. Now all I have to do now is solve this for r. So if you solve this for r, move your minus 200 over, then divide by 4 pi, so you get r cubed. Actually, I meant to say r cubed. Solve it for r cubed, and you get r cubed equals 200 over 4 pi, which is 50 over pi. Now that's for r cubed. So then if I want to find r, I have to take the cube root of that. So take the cube root of 50 over pi, and I finally get my answer for r. The radius should be 2.52 feet, rounded to 2 decimal places. Now here's another problem. The company wishes to manufacture a box with a volume of 52 cubic feet that's open on top and twice as long as it is wide. Find the dimensions of the box that can be produced using the minimum amount of material. So again, I want to minimize area. Let me just remind you that the box is open on top. So this part right here, we don't need any piece for that. Okay. So now let's talk about our primary equation. We know we want to, our primary equation is area. So we know we want to minimize the amount of area, surface area of this box. But before we get to that, let's talk about our secondary equations. One is pretty simple. One is that the length is twice the width. So we know that equation. And then the other equation is that the volume must be 52. So that means the length times the width times the height must be 52. Okay, I had these written in here, but it didn't really, I guess they got moved. So the height is that dimension, and then we can say this is the length and this is the width. Okay, so now, first of all, I know the length is 2w, so if I replace 2w in this formula, I get 2w times h, which would give me 2w squared h equals 52. And so now if I divide both sides by 2w squared, I'll get h equals 26 over w squared. Now, the reason I wanted that was because I know the length. I now have the length in terms of w, and I also need the height in terms of w. So now I've got the length and the height both in terms of w. Now, if you add up the areas of all of the faces of this box, then let's go down here and look at the area so you can see where I got this formula. Okay, so here I have 2 times L times H. Well, that would be, LH would be this side and then the back side. And there's 2 of those. So I have 2 times L times H. And then the area of this side here, that would be WH, and then there's another side on the left, WH, so there's 2 of those. Now I don't have a top, I just have a bottom. So the bottom is length times width, so I only have 1 of those. Okay, now I can do my substitution. So I can go in here, and everywhere there's an L, I can replace it with 2W. So here I would replace L with 2W there. And where there's an H, I can replace it with 26 over W squared. So I'll replace the H with 26 over W squared. And then here, I don't have an L, but I do have an H. So replace that H with 26 over W squared. And then here, replace the L here with 2W. Now, multiply all that together. 2 times 2W plus times 26 is actually 104 over W. And then 2 times 26 is 52. And then that's going to end up with be 52 over W, and then 2W times W is 2W squared. Now these two have the same denominator, so let's just go ahead and say I can add them together and get 156 over W. And now I'm going to write this area. Instead of putting 156 over W, I'm going to do what I did on the previous problem and write that as 156 times W to the negative 1 to make it easier to differentiate. Now if I take the derivative of this, I get my A prime to be minus 156 W to the negative 2 plus 4W. And then if you set that equal to 0, you'll get minus 156 W to the negative 2 plus 4W equals 0. And then I'm going to multiply everything here by W squared so that I can eliminate the W to the negative 2. So if I multiply this by W squared, it'll cancel the W to the negative 2 and give me minus 156. And multiply this by W squared, I'll just get 4 times W cubed, and then here I'll get 0. So then I can actually factor out a negative 4 here, and when I factor out a negative 4, I get 39 minus W cubed here. So finally, if I solve this, set this equal to 0 and solve it, I'll get W cubed equals 39. So W must equal the cube root of 39. And when I plug that in the calculator, I got about 3.4 feet. Okay, now, so the width is about 3.4 feet. The length is twice the width, so that's going to be about 6.8 feet. And then the height, remember, was 26 divided by W squared. So that's, plug that in a calculator, and I got about 2.25 feet. And those are the dimensions that you need to minimize that surface area. Now on the next two problems, I'm going to just show you the problem, and I'm going to ask you to pause the video and go ahead and try to work this problem. So this first problem, it wants us to find the dimensions of the field that has an area of 730 square feet that would be the cheapest to enclose. So we want to actually minimize the cost on this one. Okay, so after you've given this problem a try, then go ahead and play the video, and I'll slowly scroll through it here and you can check your work. So we know area is length times width, and length times width has to equal 730. So L equals 730 over W, and we know that the cost would be 2L times 3 plus 2W times 4, because that was given in the problem. And then if we replace L with 730 over W and then simplify that, we get a formula for cost. And then you take the derivative of your cost function, and then you solve that for W. And by solving that for W, you get W and you get L. So you can get W and L. Now I want you to do the same thing on this problem. I'll show you this problem, and then you can pause the video and you can try to work this problem. Okay? So just pause the video, and then when you're ready to check your work, then go ahead and hit play. Alright, now I'm going to go ahead and scroll here. Basically what you want to do here is you've got a sheet of paper, and you know you've got a print area of that sheet of paper, and the margins of the page, the margins at the top and bottom of the page are 2 inches, so you'd have a 2-inch margin here and a 2-inch margin here, and the sides would be 1 inch, so you'd have 1 inch here and here. Okay, and you want to know what dimensions will minimize the amount of paper. So I'm just going to summarize here. You can actually find the you can let the dimensions of the original sheet have width X and Y. So we'll say this is X, this is Y. And then so the dimensions of the print area would be X minus 2 and Y minus 4. That's by subtracting the margins. And then you want to actually minimize the amount of paper. So you minimize XY, and then you replace Y with 30 over X minus 2 plus 4. And that comes from the fact that when you multiply these together, you should get 30, and then you can solve that for Y. And then you've got your area. Then you take the derivative of this, set the derivative equal to 0, and then solve it for X. So X is about 2 plus the square root of 15, which is about 5.9 inches, and then you plug it back in here to get your Y value, which is about 11.7 inches. And that's it. So the answer is approximately 5.9 by 11.7 inches. And I'll work some advanced problems on the next video.